Hello, everyone. I wanted to do a quick screencast about power and work, or rather the relationship between the two. So hopefully this won't take too long, but just wanted to emphasize some things because people have sent me some questions. Um, but very basically, these are the equations that are in the chapter. We have power, which is related to work by this equation, or rather, I guess I should say energy. So we have a change of energy, which we talk about it as work, divided by the amount of time that it takes to do or to perform that energy. Um, and so that's where this W over T equation comes in. And this is in joules per second, which which becomes watts. I guess I should actually put that in there. Um, these are the units of power, which is, well, this is the standard unit that we use, which is watts, which is again joules per second. And that helps us remember that it's energy per second, or the change in energy. And we know it's the change in energy because we can relate work to this change in kinetic energy, which is the work energy theorem, also talked about in the chapter. And we know that work is also this force times the angle that it makes along the line of direction of movement, which is S. It also talks about this average power, which is something important to know. We're not going to discuss it too much here, but we have this equation too, with the average power is equal to the force that's, again, moving along that direction of motion, and the average velocity of whatever object it is. So that's another way to relate energy, force, and velocity. But these basic equations is really all that we need here, is that power is related to the change in energy over time. So here's one of the conceptual questions that it asks, and we'll walk through this also. So the power needed to accelerate a projectile from rest to its launch speed v in a time t is 43.0 watts. How much power is needed to accelerate the same projectile from rest to a launch speed of 2v, so twice the speed, in a time of 1/2 t, so in half the time? Now this, in order to complete this, we have to think about how, again, we can relate energy, or change in energy, and power. And we can do this with our delta KE, our delta kinetic energy, or the change in kinetic energy. So the change in kinetic energy for the first projectile, which we will label as A, if it's from rest, so the initial kinetic energy is 0, and the final kinetic energy then is 1/2 mv squared. So that v is the velocity. If we want to find out how much power it required to get it to this kinetic energy, then we divide by t. So that's what this lower equation is. So the power, which we are given is 43 watts, is equal to its change in kinetic energy, which is 1/2 mv squared, over time. So this equation is the power to get the first projectile up to a speed of v. Now we're looking at the same projectile, and we want to launch it now at a speed that is twice as much as the first time, and we want to do it in half the time. So we can still set up the same equation. We have our delta KE b, which is for the second time. And the final velocity, we want now twice the velocity. Now notice that we included this 2v inside this square. We didn't just do a 2 times v squared. It's actually twice the velocity. So we need to include that 2v inside this square here. And so we can then get, if we divide it by the time that we want to do it in, which is now 1/2 t, we can set up our equation. So P is equal to delta KE, which is 1/2 m, now 4. That 4 comes from that square of the 2v squared over 1/2 t. Simplifying this, we get, and there's a reason why I kept it like this, and I'll talk about it in just a second. We have 8 times 1/2 mv squared over t. So another way we could write this is basically the 1/2s could cancel out, and we would have 4 times mv squared over t. But the reason I kept it like this is that it helps us see the relationship between PB and PA. So this 1/2 mv squared over t is the same form that PA is in. So therefore we can write PB is equal to 8 times PA. So the power that we need in the second instance is 8 times the power that we needed in the first instance. And so now we can just simply do 8 times 43 to get 344 watts for our final answer. But hopefully that helps clarify some things. Again, we really like to keep things in as much of a variable form as we can, and then try to find relationships between things. So you will probably come across some of these types of problems. So look out for that and be aware. If you have questions on this, please leave comments so that everyone can participate in a discussion on this. If there is something else that you'd like some clarification on, please send that to me. And hopefully this helps and assists. So thanks. We'll talk to you later. Or we'll talk to you later. We'll communicate online later. Thanks.